Hi, my name is Jingyun, a doctoral student from Tsinghua University. I'll introduce my work on knurling what is worth knurling, active and sequential domain adaptation for multimodal gross tumor segmentation. Accurate gross tumor volume segmentation on MR images is critical for therapy planning in carcinoma, like the precise delineation of the surgical margin. Recent advances in deep learning have brought promising results in automatic medical image analysis, yielding successful models for various segmentation tasks. Unlike large natural image datasets with annotations, the general capability of these medical models is limited by the large variability in training data and the lack of label data. One approach to ensuring reliable and robust model adaptation is active domain adaptation, where the most informative samples are actively selected to be labeled and fine-tuning the high-performance models with as few label samples as possible. But previous active domain adaptation methods presuppose access to source data, an assumption that often fails in medical imaging due to regulatory constraints and ethical concerns. And static one-off selection schemes can easily cause negative transfer, and no works fully exploring the multimodal medical images, such as a multi-sequence MRI. To address all the above issues, we propose an active and sequential domain adaptation framework for advancing gross tumor volume segmentation on multimodal data in a source-free manner. Specifically, in each selection round for the unlabeled dataset, we identify the most valuable samples in the current state based on our selection criteria. Then, a dominant modality election procedure is introduced to select the modality that exhibits promising performance. We quarrel the label for the dominant modality scan and update the labeled target dataset. Then we train the model using the labeled set in a supervised manner. For the selection criteria, we estimate the uncertainty, objective abundance, and the density of each sample as indicators of their informativeness and representativeness. Taking into account all these factors, we identify the most valuable sample. We quantify the informativeness by jointly considering its predictive uncertainty and the objective abundance. The objective abundance is estimated via the total predicted volume, where the summation denotes the number of voxels predicted at the foreground in the segmentation mask. The uncertainty score is computed as a mean voxel-wise entropy across all predictions for sample X. Inspired by previous work, two components in the measure are interpreted as uncertainty Q and concentration Q. The former identifies data that the model cannot predict confidently, while the latter indicates data with a higher concentration of objectives. Such samples are necessary to be annotated for precise model training and refinement. Meanwhile, we quantify the representativeness of Xi based on its density. And omega is a distance between samples Xi and Xj measured by the Wassiston distance for its ability to handle shifts in data distributions. And omega d is a neighborhood distance threshold. After the most valuable sample Xr is selected, it further undergoes a dominant modality election procedure to identify the dominant modality scan for annotation. In this procedure, a validation process is applied. For the selected sample XR, the modality that exhibits promising performance is selected to be annotated. As we can see, this scan highlights the tumor better than all the other scans. It's easier for doctors to annotate on this scan. Then we query the label for the dominant modality scan MR from the doctor. After this oracle annotation run, we train the model using the label set in a supervised manner. It is worth noting that if the model initiation is not proper to start the active learning process, it may produce meaningless informativeness estimation for the target domain. So, one-off selection based on such criterion can easily cause negative transfer. To mitigate this, we sequentially select the most valuable sample to label in each query round based on the model current state until the labeling budget is reached and we fine-tune the model incrementally. We show the compared results of active domain adaptation methods on two grass tumor volume segmentation datasets, and we also show the 3D animation compared of these results.
Ground truth of nasopharyngeal carcinoma. Ground truth vs results of hours. Ground truth vs results of ADA. Ground truth vs results of MHPL. Ground truth vs results of CUP. Ground truth vs results of STDR. Ground truth vs results of lambda. Ground truth of edema from broad TS dataset. Ground truth vs results of hours. Ground truth vs results of ADA. Ground truth vs results of MHPL. Ground truth vs results of CUP. Ground truth vs results of STDR. Ground truth vs results of lambda.
To show the effectiveness of multimodal learning, we perform ablation study on multi and single modality experiments. The results show that multimodal learning can indeed enhance tumor segmentation. Clinics often provide scans with multiple modalities since multi-sequence data is easily collected, making it more efficient to use all available data rather than randomly choosing a single modality, especially given the performance variation observed, like in ET results. Our main contributions are we propose a novel, active, and sequential domain adaptation framework. It dynamically selects the most valuable samples to learn, enabling effective adaptation of well-trained source models to target tasks in a source-free manner with as few label samples as possible. And we derive a multimodal sample query strategy for dynamic multimodal sample selection and significantly reduce labeling costs, optimizing the use of rare medical resources. And the limitations of our methods lie in the informativeness criteria, which is originally proposed for vessel segmentation task. While it effectively identifies salient regions, it tends to bias the selection towards larger tumors. So We will explore robust sampling strategies to improve segmentation performance on small but significant lesions and enhance the overall clinical unity of our approach. Moreover, our current experiments are limited to unit-based architecture, so in the future we plan to incorporate more advanced foundation models such as medical SEM. If you are interested in our project, you can email me or visit the GitHub link to our project. Thanks for your listen.